Hello everyone, I'm Professor Sever, and today we're going to investigate infinite limits. And really we'll be looking at vertical asymptotes, but most importantly, how to determine analytically whether the limit goes to infinity, minus infinity, or doesn't exist. And before we engage in that analytical exploration, let's look at an initial example graphically. Okay, so here we have our first example. And what we want to do is find the limit, if it exists, at x goes to -2, and then x goes to 2. We're going to do these problems separately. And to do that, we're going to use the notion of one-sided limits, and our characterization that the full limit exists if and only if the limit from the left is equal to the limit from the right, namely that they both exist. And actually here we'll see a modification to that in terms of infinity and minus infinity. Okay, so let's look at the graph. We want to do the limit, let's do this one first. The limit as x goes to -2 from the left. So if we're looking at the x-axis, x is going to go from -2 this way. And then while that is happening, let's look at our functional values. We can see that on that side of -2, the limits are growing without bound, and those go to infinity. Okay, so that's the limit from the left. We can see it here once again, going to infinity. All right, now let's look at the limit as x goes to -2 from the right. I'm showing you the functional values there, but x would be going this way. So as x is going that way, we track the y values, and we see that's also going to infinity. Now, the limit from the left is the limit from the right. These are the same. They don't exist as numbers, but they're the same. So then we say that this limit, the full limit, as x goes to -2 is equal to infinity. And how that appears on the graph, we see that on both sides of -2, the function is growing without bound. And certainly I've already have it labeled here. We're considering the two values for which the function has vertical asymptotes, namely x equal 2 and x equal -2. All right, let's look at the next one. Let's look and see. We want to look at the limit as x goes to 2 from the left, which is going to 2 this way. And what happens? Well, when that happens, y is going to -infinity. And we're doing this is just done graphically. And now we're doing the other limit from the other side. X is going to 2 from the right. And as that's happening, the y value is going to infinity. And now we see we have a problem or a discrepancy between these two. The limit as x goes to 2 from the left is -infinity. The limit as x goes to 2 from the right is +infinity. You can see they're going in opposite directions here. Can we say that the limit exists here? No, it certainly doesn't exist because it's not defined as a number. But as we did with the limit at -2, we can say more than it just simply doesn't exist. And this is what we would have said a few sections ago in the course. We would have just left it as the limit doesn't exist. Now, once we have these notions, the infinite limits going to infinity or minus infinity, we have to determine whether we can say something more, as we did here, namely the limit goes to infinity. Well, in this case, since these are not the same, since the limiting values here are tending towards different numbers or different directions in this case, the only thing we can say here is that the limit doesn't exist, which is what we would have said a few weeks ago. Okay, let's shift to our first analytical exploration of how do we do it when we don't have a graph. Well, we're going to look at these two problems. So notice we're considering the limit of the same function and really the same c value, which is 0, just the two sides, and then of course you would use these two limits, the limit from the one-sided limits, to determine whether full limit exists. And then we have the same thing happening on our second problem, something similar. And in fact, it's not really what we'll find out. It's kind of easy in a sense. We're not going to do 3 different problems. Our one solution will in essence answer all of these virtually at the same time. Certainly it'll be these two first, kind of together in a way, and then they will give us the answer to the full limit. So let's explore the first problem. Okay, so now here's our function First thing we need to do is find where the function is discontinuous, which in a roundabout way is similar to finding the values in the domain, or technically the values that are not in the domain, discontinuities. All right, so let's do that. So what we want to do is set the denominator equal to 0. Solve that equation. Why are we doing this? Well, it's a rational function, and we know where a rational function is discontinuous. All right, and this will tell me it's discontinuous at 0, also discontinuous at 1 when I'm solving those equations. And if we were paying attention to that question that I just said, or the statement, that algebraically we would say the domain is not equal to 0 and x is not equal to 1, and written in interval notation, this is just for side. This is how you would write the domain in interval notation. Okay, so now what we have to do is consider the limit. Now, I have all of these here, and we also need one other thing for the full analytical solution. We need to find the zeros of the function. And to do that, we set the numerator equal to 0. This is the full solution. And a lot of times you'll see, especially outside of class, because, if you're not in someone's class, you're seeing a lot of different methods for doing this. A lot of them aren't very analytical. And this is truly what we're trying to do, is develop the analytical solution where we have absolute certainty as to what's going on. Now, you remember, these techniques have been around for a long time before we had the advent of the graphing calculators, the Desmoses, where you can just go and look at the graph and get the answer, similar to how we did it visually in this problem. But remember, actually graphing the function is much more difficult than determining the limit. You determine the limit to understand properties of functions so that you don't have the burden of producing the full graph. Okay, so what we want to do here is we want to produce a sign chart. And really, this whole technique is predicated off the notion of continuity, and really it's using a theorem that at this point in most courses we haven't gotten to, but nonetheless, it's how we will do the problem. Well, kind of a naive approach is to say, well, let's just pick a number close to 0 on the left-hand side and evaluate the function there and see whether the function's positive or negative. And in essence, that's what we're going to do, but the question becomes how close it's close. And notice, you can see on the right-hand side, you would have had to have picked a number closer than 1 over 100, which is 0.01. And I could have made this, if this number would have been 1,000, then you would have had to have been closer to 0 than 1's thousandths. So anyway, here's how it works. We need to put our discontinuities, which we know they're vertical asymptotes here. Why? Because the limit as x goes to 0, let's look at the original problem. The limit as x goes to 0, the top is non-zero, but the bottom is 0. So you have a non-zero number over 0. We know this is D and E from the old days. Now what we have to do is determine whether we can say more, whether it's plus infinity or minus infinity. And we also have to include, and this is not to scale, our 0 of the function, which is there. All right, so we're going to do a sign chart. These would be open circles if we were caring, because these are really the values that are not in the domain right there. And this kind of a closed circle. Okay, and we're going to pick a test point from each of the intervals. And what we're doing a sign chart of our original function. And really all we're doing is trying to find out where it's above and below the x-axis. Why? Because we already know we have a vertical asymptote here. And this is the only place where the function is 0. And so what this is doing is, on each of these intervals, pairwise consecutively, the function is continuous and has a single sign. And that's the kind of the trick here. So let me show you what's happening. So let's take any number over here, -1. Even though we care about this side for the right-hand side, this will be the left-hand side of 0. I'm going to pick a test number from each of the intervals obtained. Okay. And then I'm going to create a little chart to plug them in. And I'm going to leave the plugging in to y'all. Pause the video or watch the video and then run through it, but I would pause it and test these values. So what is f of -1, my first test value? Well, it's -101 over 2. And we don't care about the magnitude of the value, we care about this. So, in fact, let's highlight that, okay? So what we'll do then, above the interval, this was our test value. We know it's negative as the result. So above that interval, we put a big minus sign because we got a negative result for our answer. Now, this is the part I'm going to leave for y'all, so this will be your interactive part of the video. F of 1 over 200 is some positive number. And what we want to do is put a positive number there. And f of 1/2, that should be very simple for you to evaluate. That will be negative. And you should know what it is. That's 49 over -1/4. That's -196. So we're going to put a large negative here. And for our last value, f of 2, that's a positive value. So I'm going to leave this for the viewer. Pause the video, work that out. You'll get a positive number. It'll be 199 over 2 you should get. And that's certainly positive. Okay. So now here what we're really saying, the function's above the x-axis there. It's below, above, and below. And that's not really what we're working on. It is indirectly, because a consequence of that, and once we know that these are vertical asymptotes, as I said earlier, what has to happen here on this side of the graph, the function is going negative, which means it's dropping. It would look like this. It would be going down like that. And on the right-hand side of 0, it would be going up. That's what it means here. So, from the sign chart, what we can conclude is that the limit, as x goes to 0 from the left, we look at the left-hand interval of 0. Since that's a vertical asymptote, we get negative. So the answer is -infinity. And don't forget here, we already knew that it was a VA, a vertical asymptote. If we didn't, then the analysis would be a little different. All right, let's do the right-hand side of 0. And I put VA here. Let's back up. All right. So on the left-hand side of 0, the answer is equal to -infinity. Why? Because we already knew it was a vertical asymptote going in. It's the negative here that told us the answer was -infinity. So let's do the right-hand side of 0. And again, we're going to look at the sign chart. The sign of the appropriate interval tells us the answer. Again, here it's positive, so we know that on this side, going to 0 from the right is going upward forever. Therefore, it has to be going to infinity. Positive infinity like that, but we normally don't write that. We'll just write infinity. Now, are these two the same? The left and right-hand limits are computed. Here they are. Are these two the same? No. So since they're not the same, they're not going both to infinity or -infinity, then we only have one conclusion to make about the full limit. The full limit is d/e. And had the two one-sided limits gone to the same place, which they didn't, but if they would have, suppose this were -infinity, then these would have been the same, and then that would have been your answer here. Okay, that's the first problem. In the next installment, I will do our second problem, which is a much more interesting limit, and we'll look at our second example. I'm Professor Sever. I hope you enjoyed this video, which is part 1 of the analytical techniques in this section, and we will continue with this video in the second installment, and then work on a little more complicated example for our third analytical technique. We'll see you next time.